Okay, so let's again work in the setting of a metric space. But remember that the metric spaces of interest to us are mostly going to be the Euclidean space and its subsets. Okay, so today we talk about compactness. So take a metric space and I'll name the metric ones. X is called if it satisfies the property that you saw about the closed interval in the last semester. So what is the definition? It's called sequentially compact if every notice in particular that if every sequence in X itself has to have a convergent subsequence. Our entire world is X. So this convergent subsequence, that means it has a limit. So where must this limit be? And the limit must be in X itself. There is nothing else. This comment may appear strange, but the reason why I'm saying it is that, so remark. So this is a definition. So this is often so if I have a metric space, then every subset also becomes a metric space, right? Under the same metric. So S. So note or recall that SD itself or is also a so what do I mean by S is compact? And exactly the same definition applies, which is to say S is sequentially compact if every sequence in S has a convergent subsequence. But here there is a potential for small confusion, because what could happen is that since S is sitting in some ambient space X, it could be that this subsequence does have a limit, but the limit belongs to X. Notice that the definition does not allow such a thing. So is also a metric space. And so it's not compactness. So for S to be sequentially compact, limit of the definition at the bullet point is complete. I mean, it's correct in itself, but this is something to keep in mind. See, for example, open interval 0, 1 is not compact. Every sequence in open interval 0, 1, every sequence that is contained in the open interval 0, 1 is going to be a bounded sequence of the real line. As such, it is going to have a convergent subsequence. But the limit of that subsequence need not belong to the interval 0, 1, right? For example, if I just take the sequence 1 over n, So open interval 0, 1 is very far from being sequentially compact. All right. So, okay, so here is the thing claim. Let me just state this. The sequentially compact subsets of Rn are precisely those that are closed and bounded. Now, the word bounded has to be understood carefully. What do I mean by a bounded set in Rn?
It's a set that is contained in some box, where a box is a product of closed intervals in R.
Right. Okay. So that's a very reasonable definition, and we will write that down. But you see, the notion of bounded means there should be some kind of bound given by some number. I mean, intuitively speaking. And if I want to say that something is bounded, then that is going to depend on, let's say I'm trying to do this in a metric space. Then the notion of boundedness is going to depend on the notion of distance. So in Rn, if I want to say that something is bounded, then I have to have some notion of distance. So it's going to depend on the norm. But then again, it is not going to depend on the norm, because we know that all norms on Rn are going to be equivalent to each other. We haven't proved that, but we will. So a subset K of Rn is sequentially compact Okay, so we'll say, again, definition. A subset S of X comma D is bounded So again, definition. So what's the natural definition in a metric space?
And there's a ball which contains this.
So if it's bounded in, if it's contained in a ball of some radius, so does the center of this ball matter? Just notice a very simple comment. If a subset is contained in a ball centered at X, then it will also be contained in a ball centered at any other point that you like. Just use triangle inequality. So for example, let us say S, all points of S are within distance 100 from X. And if I give you some other point Y, then it is also going to be, then all points of S will also be within some distance of Y. And what distance? Come on, this is a simple question just to check if you are awake, so to speak. So every point of S, so fix a point X, fix a point Y. Let us say that every point of this set S is within distance 100 from X. Then every point of S is within what distance from Y?
100 plus the distance between X and Y.
And that's just triangle inequality. Right? So, okay. Again, notion of, so just remark, note that boundedness okay, that sentence did not start out well. What I'm saying is that this notion a priori depends on the metric. Okay, boundedness depends.
Hello, sir.
Yeah, let me just finish the sentence and I'll come back.
Okay.
So note that boundedness depends on the metric, but it is also true that if I have two different metrics, they will give me the same notion of boundedness. That is, a set will be bounded with respect to one metric if and only if it is bounded with respect to another metric. Under what conditions? We have one sufficient condition to say this.
The equivalence of them.
If two metrics are okay. Now this is a slight issue. We didn't really define equivalent metrics, correct?
Yeah, so we
Depend on the equivalent norms. So you can imitate the definition. If two metrics are, so I'll just put this equivalent. There are, which is to say that the distance between any two points, according to one metric and according to another metric, they are always within a fixed ratio. Are equivalent. So I'm going to say analogous to okay.
Sir, can we use that same definition that we use for norms, that there exist two constants alpha and beta?
Exactly. That's what I mean by analogous to equivalence of norms.
Okay.
Yeah. Okay. So this is a fairly easy comment, which you should sort of see for yourself. In any case, for us, we are going to be mostly in the setting of normed linear spaces and their subsets. So, okay. So, any questions so far? So just see for yourself that now the claim makes complete sense. Okay.
Sir, in the definition you said the small x is any element of the metric x, right?
Yes. For
Okay.
some. All right. And we will also make another definition. So again, definitions. All right. Okay, so instead of making further definitions, let's maybe prove this, proof of the claim. Okay. So we will do this in steps. So the first one is to say that proof in steps. So one, a closed interval, let's say A comma B in R, is sequentially compact. So what is the proof of this? Do you recall? So suppose I'm given so let's say I'm given a sequence. So given a sequence, x1, x2, let's say in R, before we even go to the closed interval. So what is the key property? And this is where, I don't know what proof you saw, but one very nifty thing is that given a sequence of real numbers, I can always extract a particular kind of subsequence. Anyone?
Supremum exists, so we can always find a subsequence that approaches to the supremum.
No, so there is no
Monotony.
Yeah, exactly. So you see, this sequence this is a sequence of real numbers. It may or may not have a conversion. It may have absolutely no convergence properties. For example, consider the sequence 1, 2, 3, 4, and so on. However, it is true that given a sequence of real numbers, I can always extract a monotonic subsequence from it. Monotonic.
Even though there's no supremum, the lim sup will exist, right? Lim sup and lim min.
Okay, all right. So, okay, fine. But okay, so can you say that you can always extract always an increasing subsequence? That's just not true, you see. For example, your sequence could be -1, -2, -3, and so on. You cannot extract an increasing subsequence. So you have to be a bit careful. In that it could either be increasing or decreasing. So, okay, so you can use, but here, sort of in simple words, you can say that, so here's the thing, as follows.
It need not be a strict monotone.
Yeah, it need not be strict. For example, just you could say your sequence could just be a constant sequence. So a weak monotonic subsequence. As follows. So, so we call a term, or we call an entry a term xi to be a peak if xi is, let's say, strictly greater than xj for all j greater than. That means once you attain this level, then everything else afterwards is lower. So now there are two cases. If number of peaks is infinite, then what? Then notice I have the first peak wherever it occurs in the sequence. So I take that. Then I take the next peak. What is going to happen? The next peak is going to be, comes after the first one, no? So it has to be strictly smaller. So I take the first peak, then I take the second peak, then I take the third peak, and so on. The sequence of peaks, in fact, is going to be strictly decreasing. Okay. So if number of peaks is finite, then what do I do? That means that at some point, I cannot really find any further entries with this property. There is no further peak. But what does not having a peak mean? It means that no matter which term I take of the sequence, there is going to be something later on that is going to be at least as big. So what do I do? How do I extract this subsequence now? The monotonic subsequence now is going to be a weakly increasing sequence. What should I do? What should be its first term?
A term that is greater than one of the peak.
Right. Or by greater than, you mean not in size, but in index, correct?
Yes.
So exactly. Then let's say y1 is equal to a term after the last peak. And then having chosen yi plus 1, a term after yi. Such a term must exist, you see, because if no such term exists, then that means yi would be a peak, but I have already gone beyond the last peak. And then y1, y2, etc. is a weakly increasing subsequence of the original sequence. So why does this do the job? Notice that, so I never use closed interval until now. So now suppose this sequence is in the closed interval from A to B, then how does this, whatever I said, how does that help me? I extract this monotonic subsequence. And now, by virtue of this entire sequence being contained within two bounds, what happens? Come on, this is all from the previous semester. You have a monotonic increasing sequence or monotonic decreasing sequence, as the case may be. Then what do you know about convergence? You immediately get to assert that such a thing converges
By bounded above or below.
Right. So this is exactly the sort of completeness of real numbers, right? A monotonic sequence is going to converge. Monotonic increasing sequence is going to converge exactly when it is going to be come on. A monotonic increasing sequence of real
Bounded above
numbers, right?
in R.
Right. It's when it's bounded above. So I'm just going to say, and what is it going to converge to? We can even say what it's going to converge to.
The supremum of it.
Exactly. So it's going to converge to the least upper bound. And likewise for a monotonically decreasing sequence, it is going to converge to its greatest lower bound, infima. So when xn is contained in A and B, by boundedness of this monotonic subsequence, it converges to its okay, so use or GLB, LUB if you prefer that. So are we done? Notice that, see the definition of sequentially compact. Are we done? Have we proved that the closed interval is sequentially compact?
Have we shown that the sequence lies in the interval? I mean, it does, but have we shown that now?
But again, see the definition. It says that, sorry, we should go to the definition. X is called sequentially compact if every sequence in X has a convergent subsequence. So you see, in order to show that a subset of R is sequentially compact, I start with a sequence in that set. Right. Okay, so let's write down a sentence here. Take a sequence xn in AB. All right. So what do I need to do? Again, let's go back to the definition. I need to extract a convergent subsequence, but this convergent subsequence has to be convergent in the metric space that I'm working in. So my metric space here itself is the closed interval. So what extra bit needs to be said here? Okay, so clearly I'm not being, I'm not being transparent over here. This is, yeah, go ahead, please. Yes.
The supremum and infimum of the interval is in the interval.
Right, exactly. You see. And the limit is in Is it clear that the limit is going to be in this interval? Or does it require some serious proof?
Sir,
Yeah,
sir, in the definition, we did not actually explicitly mention that it needs to converge in a point within the interval. So why exactly are we checking it?
exactly. So let's see this once again and notice the parenthetical comment. The definition as stated is complete, is correct. However, when I'm applying this definition to a metric space, every sequence in X has to have a convergent subsequence. But of course, if the sequence is convergent, my world itself is the metric space X. What does it mean for something in a metric space to converge to something outside the metric space? If the only thing that I have is X, then that statement is nonsensical. Okay.
Oh, yes, sir.
However, the question is really valid because often I am going to apply this. This is what the parenthetical comment is. Often we are going to apply this to worry whether certain subsets of metric spaces are compact. In which case, what we have to say, what does this mean? Because this subset itself is a metric space, the definition means that I have to take any sequence in S and I have to see if I can find a convergent subsequence in S. But of course, the limit has to be in S, otherwise the definition makes no sense. Okay, if you want to remember it like this, you should remember has a convergent subsequence whose limit is in X. Maybe you want to remember that as an extra phrase. Applied to a metric space in itself, it is nonsensical, or rather that phrase is redundant. Sometimes it's like when you define groups, sometimes people say that a group is something that has that is closed under a binary operation and with some properties. For the same reason as here, that statement is nonsensical. What does it mean for it to be closed? Your group, your set G becomes a group if there is a map from G cross G to G. What does it mean for it to be closed? There is no ambient set that you're talking about. But one thinks like this sometimes because one is thinking about whether a subset of a given group is a group within itself. In that case, this closed business is, I mean, you can think in those terms. Okay, so this is a very simple point, but don't get confused about this. Okay, any other questions? All right, so coming back to this last point, and is it clear that if I have a convergent sequence in the closed interval, then its limit must also be in the closed interval? Okay, and I sort of insist on stopping here because you did, after all, analysis 1, and we are supposed to build on this. So, okay, suppose I have a monotonic increasing sequence in the closed interval A, B. Show me that it converges to something in the closed interval A, B. Come on, this should be quick.
So it converges to something, and if that thing is out of AB, then the whatever like is without loss of generality, it's greater than B. You can just take whatever difference it has with B, and no term could have been within that difference.
Right, so you can apply the epsilon definition. Okay, do you really have to do this by contradiction? Well, you see, the point is that what is this limit? When you prove that this has a limit, the limit is going to be the supremum, right?
Yes, sir. B is a upper bound, so it has to be less than that.
Exactly. So B is an upper bound for everything in this increasing subsequence. So its supremum is also going to be less than or equal to B. Okay, whichever way. And likewise, if you are taking the infimum of a decreasing sequence. Okay, so this was step 1. But remember what we wanted to say. A subset of Rn is sequentially compact if and only if K is closed and bounded. So we still have quite some distance to go. We showed that a closed interval is sequentially compact. So we are sort of proving the backward direction that some kinds of sets are sequentially compact. So from R, how do we go to Rn? So let us say A1, B1 cross AN, BN. Can we see why?
So from the theorem that we proved in the last class.
Right. So you see, we want to say something or the other about there being a convergent subsequence. But we did prove something about, so recall, that if I have a sequence xn bar converges to x bar. Oh, this is bad. Let's, because n is my dimension. So let's make it m. So I have a test, a slot-wise test, right? If I don't leave the sequence in each coordinate, which is to say, if I take xm and if I take the ith coordinates, then that should correspond, this is a necessary and sufficient condition. And you remember what was useful over here?
The equivalence of norm.
Right.
Norm.
Exactly. The equivalence of, so is sequentially compact. And so really speaking, under the with respect to any this we can show because these norms are equivalent. So the notion of convergence stays the same. And later on, we are going to say that actually it will be true for any norm. So let me just add that. And the one that we used was the max norm, right? For p equal to infinity. So is this easy now? I claim now this is easy. So take a bounded sequence. Take a sequence in sequence in the given box. I need to extract a convergent subsequence whose limit is also in the box. So how do I do this? Come on. Okay, so all right, so this sequence is going to be first is going to, I mean, it's going to be a sequence of vectors, right? So if I first concentrate only on the first slot. If I look at just the first entries, then that is going to form a sequence. And this sequence is going to lie, it's going to be a subsequence of real numbers, but in fact, all of these entries are going to lie between A1 and B1. So this is the bounded sequence of real numbers. It is going to have a convergent subsequence. So I extract that convergent subsequence and I take the corresponding terms in the original sequence. So what do I have? I have the original sequence and I have a subsequence of it with the property that the terms, if I just read the first slots, then that sequence converges. Continue. That is, from this sequence, now I extract a subsequence whose terms in the second slot converge, and then continue. And after n steps, I will have a sequence such that in every slot it converges. And slot-wise convergence is enough to show that the entire sequence converges. Right. So let me write this down in a function. Extract whose by means of step 1. And where do they have to converge? Necessarily to something in okay, so maybe let's give a name to it. Necessarily to some x upper 1. And now just continue. From this subsequence, further in second slot. And continue. Okay, so we have that boxes in Rn are sequentially compact.
We are talking about matrix space defined on a vector space, right?
Yeah, so I'm not sure I understand the question. So what do you mean?
I mean, here we are taking Rn. So, I mean, metric on a vector space, we considered that. So, can the vector space have infinite dimension and still this property hold? Like the function, the space of the vector space of functions with some inner product, that integral inner product or whatever.
Okay, so one is that this is beyond our brief, but just notice, if I have an infinite dimensional space, then the notion of convergence itself depends on the norm. There are multiple inequivalent norms.
Yes.
Right? So compactness is an extremely important notion, even in infinite dimensions, and you will see more of it in topology. Maybe we'll have some brush with it, but right now I don't want to say anything more than this. Okay, so let's go on. So we were working towards the backward direction. We have showed that a box in Rn is sequentially compact. But from this, now we have to show that any closed and bounded set is sequentially compact. So there seems to be quite a bit of gulf, right? To go from just a box that is a closed box, a product of closed intervals, to an arbitrary closed and bounded set. Any ideas about this?
So I think it will be true for norms because it's like a box will be like just it's a closed set in like infinity norm, like uh, then like because all norms are equivalent, we can tell that any other like a closed set with respect to any other norm will also be like closed set in like an infinity norm. I'm not sure exactly.
Right. So what you said is correct. However, you see our proof is really very closely attuned to the closed interval. Two things, the closed interval in real numbers, and after that, just ability to separate closed intervals in each slot. So for example, just if I give you the closed ball in the Euclidean space, let's just say in R2. So an ordinary circle, I mean the interior of the circle along with its boundary. That is the closed ball, right? It is bounded. Let's say I take a ball of radius 1. It is bounded because by my definition, it is contained in the open ball of radius 2, let's say. Is it closed? This is one question. Huh? Is a closed ball in a metric space a closed set? Did I assign this as an exercise until now? Well, if not, you should think of this. The answer is yes. Again, because of triangle inequality. But anyway, so let us say I take the disk in R2. Is it sequentially compact?
Sir, could you repeat the question once?
The question is, from this box, how do I go to an arbitrary closed and bounded set? All right, so what I'm going to do is,
Sir, we could show that every closed subset of a sequentially compact set is sequentially compact itself.
okay. All right, so every closed okay. So first, why is this true? But let's put that on the back burner for a moment. Will this do the job? Suppose I prove that every closed subset of a sequentially compact set is sequentially compact. Does this do the job? Notice, what do I want to show? That I want to show the backward direction. That if a set is closed and bounded in Rn, then it is sequentially compact. This will do the job, no?
Yes, sir.
Because you see, okay, so first you have to show that
Sir, can I say?
let me just write down something. So this this will show. So I'm going to first say that this is an exercise because we are going to do something related. Yeah, I sort of got carried away a little bit. Our main brief is not sequential compactness, but we want to define compactness, which is a by far more versatile notion, even though for metric spaces, it turns out to be equivalent to sequential compactness. So I want to sort of quickly make our way towards that. So this step 3, I'm going to leave as an exercise, but let's try to say, so this will show that each closed and bounded subset of Rn, maybe just for emphasis, of the Euclidean space, because if I have a closed and bounded subset, if I show that it is a closed subset of a box, then I'm done. So is a bounded set a closed subset of a box?
Yes, and
Sorry, one second. A bounded set is a subset of a box. You see, the set is bounded, therefore it is going to be contained in some balls. So just play with the norms. You know that boxes contain circles. You know, whichever norm we use, it doesn't really matter. But one more thing has to be said. Each closed and bounded subset because K is no, sorry, one second. Sorry, I'm just a bit confused over here. So what are we trying to show? We show that each closed and bounded subset of this is sequentially compact, because if I'm given such a key, sorry, I'm just
Just every closed and bounded subset is contained in some box. And from
yeah. So so each, so because
and it's closed in that box. So
right, and then the only extra thing to say is that a box is closed, right? Which strictly speaking, we have not really done so far. So sorry, it's each, not subsequence. Because such a set no, actually, I don't even need to show that, because you see, this is a closed set, right? So closed set contained in a subspace will continue to stay closed in that. So the only thing that has to be observed to do this is that a bounded set is going to be contained in some box. That's all that has to be said. Okay, so let me leave this, but it's now, it's the other direction that I want to. So, so proof of the forward direction, which is to say that a subset is sequentially compact should imply that it is closed and bounded. So is this difficult? I.e., if K is sequentially compact, then K is closed and bounded. So I claim that this should not be difficult. Can you see why?
K should contain all its limit points.
Exactly. So why closed? So if K is not closed, then some limit point x of K will not be in K. Okay, is this clear why? Why? What does limit points and closed set have to do with each other?
Set is closed set. The closure of a closed set is itself.
Right. So remember that closure of a set is the smallest closed set containing it. So if a set K is closed, then it is its own closure because it is the smallest closed set containing it. But then we bring in another thing. So what was the closure of a set? It was the set itself along with its limit points, right? So now this just gives it to us, you see. Then some, but now if K is not closed, then that means that some limit point will not be in K, and now there will be a problem. Then a sequence, but what does it mean to be a limit point of this set K? It means there is a sequence in K
So that converges to a point outside it,
right?
and hence all its subsequents also.
Right. So limit point of a set is a point that consists of a point such that there is a sequence, all of whose terms are distinct from that point, but which converges there. So then a sequence, let's say yn in K converges to X, but that's to X which is not in K. But you see, every subsequence of yn will also converge. Limit of a subsequence is limit of the whole sequence for convergent sequences. So it cannot possibly have a convergent subsequence in the given metric space, you see. Violating sequential So that is for the closed. And for bounded, it's sort of even easier. You see, if this set is not bounded, then there is no hope. Just think of real numbers. If some set is not bounded, then you can just construct a sequence that will have no convergent subsequence. Notice that a convergent sequence of real numbers, or for that matter in any metric space, has to be a bounded sequence. Is it clear? A convergent sequence has to be bounded. Pick some epsilon, then eventually all terms are going to lie within the distance epsilon, no, from the limit. And only finitely many terms are missing. So if I take the limit, then take epsilon and take the maximum of the finitely many distances of the missing terms from the limit. That will give me the bound. Okay. I hope you should have done all of this, no, in your analysis one. A convergent sequence is of course bounded. So how do I, so if take, let's say X sub m in K with, let's say, norm of xm greater than or equal to m. I mean, not only is this sequence unbounded, in fact, any subsequence is unbounded, so cannot be convergent. Okay, so just look at this proof. And I have a question here for you. Is this proof specific to Rn, or will this part of the proof, that is item number 4, the forward direction, will it work for any metric space?
This works for any metric space.
Okay, so observe. Number 4, step 4. So that is to say, claim if x t all right, let's do this in terms of
Sir, how did you use the definition of K being not bounded with the norm of xm being greater than or equal to m for any m? I did not understand how that is the definition of K being bounded.
right. Okay, so very good. So we were in Rn, right? So let's see what the definition of something being bounded or not bounded is. So where did we write that down? Yeah, so a subset is bounded if it is contained in a ball.
Oh, okay, sir. So the thing that you mentioned, that if it is within a certain distance from x, then it is also within a certain distance from y.
Right.
So that you
So-
took as 0 simply.
Right. Exactly.
Okay.
Exactly. So yeah, thanks for pointing that out. So for a metric space, I have to make a small adjustment over here. Instead of norm, I have to take a ball. But really, the ball can be from fix any point and take and take distances from that point. So claim if K is a sequentially compact subset of then K is closed and bounded in X. Proof, same argument. And maybe I can say use xm such that distance between some fixed x okay. But
So-
now,
So what
yes,
we
go
do, so what do we do for metric spaces which are, for example, finite sets or something?
okay,
And
so
then
very good.
sequences and subsequences.
So okay, I'm not sure I understand the question. So what is the setting and what is the question? So you're saying that you have a finite set.
Yes, which is a metric space.
Okay.
So then sort of it feels like then limit points might not be so well defined because
Okay. So very good. Let's just think about this. Let us suppose I have a finite set inside a metric space. Okay. And let's just take a finite set inside R. Okay. What are limit points of this finite set?
so only the sets which are in which are only the points which are in the set.
Right. So let's think about this a bit carefully. If I take complement of a finite set in R or Rn for that matter, what kind of set is it topologically? Just visualize. By taking a small enough radius around any point that is not among these finitely many points, I can miss all of these finitely many points, right?
Yes.
So what we are saying is that the complement of this finite set is open. So what this is saying is that a set consisting of finitely many points is closed.
Okay, so then infinite sequences will
Right. So an infinite sequence in over here, which takes values from finitely many things, has to have a constant subsequence. Because some point has to repeat infinitely many times. So that there is your convergent subsequence.
okay, so thank you.
All right. Another sort of interesting thing over here is that so then we can say, oh, look, we can be a bit greedy and we can say, look, the backward direction really worked. Sorry, the forward direction worked not just for Rn, but for any metric space. So the question is the other direction also true for any metric space? That suppose I have a closed and bounded subset of a metric space, then it is automatically compact. Sorry, sequentially compact. So question. So question. Is the same, is the other direction. Oops. So K keep saying this. And the answer to this question is so this is not true. So example. All right. So I sort of got carried away a little bit with this sequential compactness. To draw a line under what we did, we have shown that a box is sequentially compact in Rn. And we've shown that any sequentially compact set in Rn has to be closed and bounded. And we've sketched the little bit that is remaining in step 3. But what I really want to do is go to compactness itself. So let's draw a line over here. What I'm about to define may not appear so useful or may not appear to be worthwhile to define. Like, why would one define something like this? But for now, you should just believe that this is an extremely useful and versatile notion. And this is the notion of compactness. So we say the following. Definitions. Okay. So I have a family of subsets of the metric space X. So we say that this family is a cover of X if the union of V alphas is equal to X. And we say
is equal to or contains X.
Notice that my world itself is X. This is the exact same issue
okay.
as we said earlier. So we will have to see what happens to subsets later on. Okay. And we say that is an open cover if is open. Of course, in X. So now the definition is X is called compact if each open cover of X has a finite subcover, which is to say V alpha 1, V alpha 2, up to V alpha n.
So isn't it sufficient for the cover to contain X?
This is exactly the same. This is exactly the same issue that was. But where is this happening? What is this thing outside X? The only thing that I have is
okay. Yes, sir. Yes.
Okay. So just as we dealt with this issue for sequential compactness, we will deal with the same issue over here. With the union of So since we are out of time, let me just make this comment over here. So exercise. Formulate what it means for a subset K of X to be compact in terms of open sets of X. The issue is the following. K in itself is a metric space. So the definition that I have made is in terms of open sets of K. That a cover of K by open sets of K should have a finite subcover. However, what are open sets of K?
Open sets of X restricted to K.
By restricted, you mean
intersection. Yes.
Intersected with K, correct? Because again, remember, open sets of K are unions of balls in K. But a ball in K is just the intersection of a ball in X intersected with K. This is why open sets in K are just intersections of open sets of X with K. So the definition that we had earlier can be rephrased in terms of open sets of X. And this is something that you should do for yourself. So this is one exercise. And second thing is that this is a nice exercise. Follow your nose, and at some point you have to make some clever thing you have to do. Okay, it's compact in R. And 3. And the fourth one is box is compact in R. So this is really just following the earlier definition. Sorry, just bear with me for a moment or two. Any so 3 plus 4 imply that a closed bounded subset of Rn. So this is the analog of the steps 1 through 3 that we did last time. Okay, so maybe you know what? This. Let's keep the parallelism. So this is 0, 1, 2. 1 plus 2. Sorry, no, this is 3. This is exactly the parallel development to what we had above. And what will be number 4, just like above. Sorry. In any metric space X, a subset K is sorry. Then K must be closed and bounded. But just like we saw, and finally, for metric spaces, compactness and sequential okay, so it's well past time to stop, so let's stop.
Recording stopped.
Yeah, so next time we will just take all of these, but it will really be helpful for you if you try to do some of this on your own. So it really is a development.
Sir,
see what you can do, and if you can also read. Yes.
Sir, can you take the fifth statement?
Sorry, what statement?
Fifth statement. The last.
Fifth statement. Yes.
So are we supposed to prove this separately or?
No, sorry. Say that again.
Sir, are we supposed to prove this separately? Like, won't it follow from all the other?
No, I'm not really sure what you mean. Separately means what?
It will follow from all the other statements, right?
Okay, so
no.
I don't quite see how.
Okay, so yeah, okay,
right.
Okay. Set is sequentially compact if and only if it is compact.
In any metric space.
Okay, so yeah.
Any metric space whatsoever. Whereas, okay, notice one thing, I should say. Parts 1 up to 3, they really are to do with the Euclidean space. It's not about a general metric space at all. It's about a very specific space. And parts 1 up to 3, those are the things that are really important for us. Now 4 is a converse of that. And the converse is much easier. And that converse is true for any metric space. So if I put 1 through 4 together for Rn, then what we are saying is that for a subset of Rn, the following are equivalent. And if I put 5 also together, for a subset of Rn, the following are together. Following are equivalent, with the Euclidean metric. But you can have another norm also, metric from another norm. Is that this set is compact, this set is sequentially compact, and this set is closed and bounded. That is the upshot of everything that we stated. Okay, anything else? The definition of compactness takes, it takes some getting used to. So we will begin with that definition next time and prove everything carefully. But it would be really useful if you see some examples for yourself, and especially this exercise 0, please do try to work it out on your own, just to get used to what the notion is. Okay, are there any other questions? Right, so in the comments, people have offered some examples for showing that for a general metric space, a subset being closed and bounded is not enough to it does not really ensure that the set is compact. And this is kind of a simple example. So let's just discuss this because it's written down. So it's R equipped with the discrete metric. So let's take this one by one. You do not have to take real numbers. You can impose a discrete metric on any set. This is the metric that says that the distance between a point and itself is 0, because it has to be. And the distance between any two distinct points is 1. Okay. So if you want, you see every graph is going to give rise to a metric by means of shortest distance. So if you want, this is a graph in which I have taken the set of points as vertices and I have taken the complete graph. And the shortest distance is 1 between any two distinct points, and the distance between the point and itself is 0. Okay. So, all right. So what is a bounded set here?
Sir, won't you infinite graph? Because if the number of vertices is finite, then it's obviously compact.
Right. Because so let's go one by one. Yeah, of course you're right, because everything is compact. Everything is finite. The total number of subsets of a finite set itself is finite. So no matter what topology you put, the number of finite sets, the number of open sets is finite. So finitely many of them will cover any subset. So yes, but if I have an infinite set and if I put this discrete metric on it, then just notice, what are the open sets here? So maybe let's write this down. I should say that for our interest in this course, none of this is really, well, maybe it's marginally relevant because you can embed such things maybe in Rn, suitably large n. But our goal is not to do topology for its own sake. Even inside Rn, our goal is to do calculus. So this is of limited relevance for us, but let's see. So discrete metric on any set S. So you say D between X and Y is delta XY. Which is to say the distance is 1 if the points are distinct, and 0 if they are not. So this is obviously a metric. You know, it's symmetric. Distance is 0 if and only if 2 points are equal, and triangle inequality is obviously true. Just check. All right. So what are the balls in here? What is the topology? So induces what topology on S?
All subsets are open and closed.
Right. So every subset is open because, for example, so exhibit to me why a given set X, a singleton set X, is open.
A ball of half radius around X.
Yeah. So take a ball centered at X of radius anything less than 1. Remember, in a metric space, I'm allowed to take any positive number as radius. So if I take all points that are at distance less than half, then I pick up only the point X. So by my definition, it's an open set. And arbitrary unions of singletons are open. So that means that every subset is open. Induces discrete topology.
So sorry to pick at this, but shouldn't it be 1 minus that delta xy, not the delta?
Sorry. So 1 second. Delta. So this is the this is the Kronecker delta, which is,
yes, sir. And the Kronecker delta will be equal to 1 when x is equal to y and 0 when it's not.
Oh, sorry. Yeah.
So
oh my God. Yeah.
1 minus delta xy will fix that.
Yeah. Yes. So, thank you. 1 minus. So which is equal to 0 if x is equal to y, and 1 is x is not equal to y. Thank you. So this induces the discrete topology, i.e. all subsets of S are open. So notice that when S is infinite, this is not going to be compact because I can take the cover of S by singletons and it will not have a finite subcover. So this is a dumb example. Okay. I mean, this is dumb in the context of what we are saying. Discrete topology is, it's not a useless thing. It's a discrete metric is a perfectly valid metric. Now, my question is the following though. Can you give a less extreme example? I mean, this is sort of fails for fairly dumb reasons. But I claim, in fact, it's possible to have a metric on real numbers, which induces the same topology as the ordinary topology on R. And have it be a counter example for the situation at hand.
So what is the question?
Yeah, so the question is the following. Let me make it more precise. Define a metric on real numbers. And if you know the answer, please don't say it here. define a metric on real numbers in which the entire, okay, let me not give that away because you can have some fun with it. Define a metric on real numbers which induces the same topology as the usual topology. Okay. But in such a way that there is a closed and bounded set that is not compact. Okay, so let me help you a little bit because see, I already know the answer. So, thing with mathematics is that once you know the answer, then it starts becoming obvious. To define a topology, you need to have open sets. But you see, open sets are unions of some basic open sets, right? And on a metric space, what I need is balls. But you see, it is enough for me to have balls of small radius. Because a ball of big radius can be made out of a balls with smaller radius. This is one of the things, no, that if I have any open set, it's a union of balls, but it's also a union of balls that are centered at each one of the points. So the hint is, if I want the same topology, if I simply ensure that I have all the balls for small radii, the balls are the same as the usual topology. That will give me the same topology. But I do some mess with balls of bigger radius. So maybe have some cutoff. In other words, I take the standard metric, but somehow at some point it becomes all you can eat buffet. It's like sort of you go to a restaurant and you eat up to a certain point and then you have to pay more. But at some point they say, okay, if you pay this much, then you can eat whatever you like.
Sir, would d of xy equals tan inverse of absolute value of x minus y work?
Okay, all right.
And okay, maybe so scaling it by 2 over pi if you want maybe the large, like the entire real line to be a ball.
Yeah, but you see scale. Okay, so that's an interesting thought. Think about it. I mean, the question is it going to be a metric? That's something to, the triangle inequality has to be.
Poor idea. I didn't check that. I was just thinking quite naively in terms of maybe making it finite,
right,
but in not such an extreme way. That,
so you see, right. So, okay. So that's a thought. It's a thought. So you see what he did. I mean, the distances, somehow the entire distance is can go from minus infinity to infinity. I mean, R is thought of as a set, but also as a set that is quite distinct from the set of distances. So you compress the set of distances from minus pi by 2 to pi by 2, open interval. You see if it works. Triangle inequality has to work. But what I have in mind is,
also, right. Now could I try?
anyway, so something to think about.
So,
right. Okay. So here's a thought. You can consider the Euclidean metric on 0, 1 and homeomorphism of 0, 1 with R. Okay. And that will induce a metric. So you see something similar is being done over here. However, just read the comment that by Ayan.
Sir, reciprocal works.
But of course, what we know, I mean, we don't know what a homeomorphism is, but okay, I mean, so Yeah, that's certainly one way of doing that. D by 1 plus T. Okay, so I see. So the new metric as defined is, the question is again, so this is what Srimati is saying, that if D is the, as I understand what she means is that let D be the usual distance. And now you define a new distance by D prime equals D of xy divided by 1 plus D of xy. Is it a metric though? That is the thing. This will ensure that this is, I mean, it certainly is ensuring bounded. It will always be between 0 and 1. But is the triangle inequality true? By the way, so this is sort of now, so while we are on, so let me just change. By the way, the question that I asked, it is not a particularly important question, okay, just something. But while we are on the topic of defining new metrics in terms of old metrics, or defining new norms in terms of old norms, here is something that is quite important. You see, the box was very useful because it is a product of sets. So in general, it is a very useful thing to consider how to, if I have two if I have two non-linear spaces, and if I take their direct sum. So you must have seen direct sum of vector spaces, right? Just ordered pairs of vectors, and you add slot-wise, scale slot-wise. So if I have two non-linear spaces, and if I take their direct sum, then can I make that into a non-linear space? Or more generally, if I take two metric spaces, and again I do the same thing, except here I don't call it direct sum, I call it a product. It's just the Cartesian product. Can I make that into a metric space? This is a useful thing, no? Because I'm doing the same thing for R. When we defined all those norms or metrics on Rn, first I went from R to R2. R2 is just R cross R, then that cross R. So here's a question.
LP type thing can be extended in that case too, right?
So question. If VW are
so the matrix in V comma W can be like the LP thing faded from R to R2 then.
Can we define a norm? Sorry, but think about this. Can we define a norm on V cross W? Same question with are just metric spaces. Same question if are merely all of these questions are interesting. And then there is the thing is, well, can we define a norm? And the answer is yes, you can see, you can define a norm. How many norms can we define? Similarly, how many metrics can we define on V cross W? So you can maybe think about it a bit. And when you start thinking about it, somebody said, oh, we can do something like this P norm, right? Maybe this is a way also to show why the P norms are norms just based on R2. There's one obvious thing that to try is whether for distance or for metric, you have two real numbers that are coming, right? Let us say I have something in the first slot, I have the something in the second slot. So if I have a vector small v comma small w, then I have to define its norm. Well, I have individually norms of v and w. I can try to combine them in some way. Similarly, if I have, let's say, point x1 comma y1, or let's say v1 comma w1 and v2 comma w2, and if I want to define the distance between them, well, I already have a distance between v1 and v2, and I have distance between w1 and w2. Those two are real numbers. I can try to combine them in some way. So this is sort of, you see, I'm going to R2 and I'm doing something in R2. But there are lots of things that I can do on R2. I can take the max norm there. I can take I can do any P over there. So see if it works. And if it works in general, then this also gives you a way of maybe showing that this P norm is a norm in general. And in fact, you can mix and match and do a bunch of norms, you see? Because if I show that if this procedure works in general, the questions that I have given here, and if you just show that the P norm is a norm for R2, then by iterating, you will have shown that P norm is a norm for any Rn. Just check that this works. But anyway, all three questions are interesting. That last question is also particularly interesting. How do I define a topology? If V and W have topology, then how do I define a topology on V cross W? These questions are going to be relevant for us for proving the Heine-Borel theorem. Compactness of a box. This question number 2. Compactness of the closed interval will be proved by bare hands. But then from that to closed interval to go to a box, I have to handle products. For sequences, this was easy because we proved a result that convergence of a sequence in Rn was the same as convergence slot-wise. For compactness, we have to do something else because we have this business with open sets and open covers. Not so clear less clear how this is going to work, how to reduce this to a one slot case. So sorry, this is all kind of a vague discussion, but the question that I have stated here is a precise one, so you can think about it. Okay, anything else? Very well. So let's stop for today and then we will continue on Wednesday. All right. Bye, everyone.
Thank you, sir.